The final configuration that we want to consider with our IC biasing is the multi-transistor current mirrors. And so as we can see, what I've drawn here is just our simple 2-transistor current mirror. And so the question is, what if we wanted to add more transistors to this? And so we'll see why this is useful once we do the analysis, but let's start by just labeling this one Q sub R. So this is our transistor related to our reference current, and let's label this one Q sub 1. So now what if we wanted to add another transistor? So let's say we connect to this base current. So I'm going to put a dot there just to indicate that we're connecting to that base current. And we put another transistor and we connect our emitter to the same V minus here on the bottom. And our collector becomes another output. And so this is our transistor Q2. And so of course we would have, related to this first transistor Q1, we would have some output current I01. For our second one, we now have some output current I02. We also notice that our reference current now is having to supply one additional base current. It's having to supply base current for our QR, for our Q1, and also for our Q2. So we could also label, for instance, this current here is our collector current ICR, whereas of course this is equal to IC1 and this is equal to IC2. And we could also label here our base currents. So I'll do it for these three here. So this is our IBR, our IB1, and our IB2. So we could continue connecting transistors in this fashion, and we'll talk about the implications of that here in a little bit. But let's say we just connect them out until we have some N number. So we're going to keep this general. So we've connected N transistors sort of in this fashion, all connected here at the same base, such that they all have the same base emitter voltage. So that'll be important here in a little bit. Accidentally erase that. So then we have, of course, another output here, another base current. So this we can call our I out N. This is our transistor Q sub N because it's our nth transistor. So we're still going to assume that all these transistors are matched. So assuming all transistors matched, which of course means they're identical. Okay. And so part of that we defined back at the start of this series means that they have the same beta. So like we said a second ago, all of these transistors also have the same base emitter voltage. So if they have the same base emitter voltage and the same beta, what that means is they're going to have the same base currents. So our base current in our transistor R is going to be the same as our base current in our transistor 1, which is the same as our base current in transistor 2, all the way up to our base current in transistor N. Now, if the beta is the same, we also have that our collector currents are all the same. So I in our reference transistor, Q sub R, is equal to the collector current in transistor 1, which note is also our output current. That's the same as our collector current in Q2, all the way up to our collector current in transistor N. Okay, so let's say then we want to find an expression for our I naught. Well, we can do that by doing a KCL here. We'll get an expression for I naught in terms of I ref. So KCL at that highlighted point. So we notice we have I ref coming in and then coming out. Let's scroll back up. We have our ICR coming down. And then out the right, it's kind of difficult to see, but we actually have all of the base currents for every transistor involved. So out of the bottom, we said we have our collector current for our reference transistor, and then we also have IBR, we have IB1, we have IB2, all the way up to IBN, however many transistors we happen to have in this circuit. Well, of course, we know that we said all of those base currents are equal, so we can just simplify this and say this is 1 plus N times a base current, and let's just use our IBR, for instance. And the reason we have 1 plus N is, of course, we started with Q1 here, but we also have this QR to consider, which is also going to have a base current, of course. Okay, so now from up here, we said these are matched transistors, so all the collector currents and the base currents are the same, so we can just write this as IC1, and we can write this base current as IB1. So from there, we can relate our base current to our collector current using our beta. So IC1 stays the same. We have 1 plus N times IC1 divided by beta. And then we can just factor out our IC such that we have IC1 times the quantity of 1 plus N divided by beta. So we get something that looks like that. So now, of course, we can solve for this IC1, which, remember, this IC1 coming back up here is our output current. And we know that's also equal to all of our other output currents from this line down here because these are matched transistors. So what we can do is we can then say our IC1, which is really also our I out 1, which, because they're matched transistors with same VBE, is IBO2, which is the same as the output on all of those transistors through our nth transistor. And so rearranging that equation, we see that's equal to IREF divided by 1 plus N divided by beta. And so that would be our expression relating our output currents to our reference current. And so if we wanted to find what that reference current was in terms of our voltage, we would do that exactly the same way that we did for our 2-transistor current source and that we saw for our Widlar current source as well. We'd start here, we do a KVL along this path, and we could solve for that to get our IREF. So from KVL and Ohm's law, what we would end up seeing is that our IREF is equal to, in this particular formation, V plus minus VBE minus V minus divided by R1. So that's how we could solve for our R1 or our IREF depending on what information we have. So a couple things to note about our equation up here boxed in red. So let's enumerate some points here. Okay, so we see that as our N is increasing, so N increasing means that our output is going to be getting further from our ref. So output further from our, sorry, not from our ref, from IREF. And so all that is, we can see from this equation up here, as this value gets very large, of course that's going to begin dominating that denominator, but we have it above beta, so it's going to have to get pretty large before it becomes noticeable. But as that equation, as that N gets larger, that is tending to decrease these values for our output currents over here. So that's one thing to notice. But like I was saying, if we assume that that beta is very large, but if beta is much greater than 1, essentially what we're saying is we neglect base currents, then we could say our outputs are approximately equal to IREF. Then each output current is equal to approximately equal to IREF. So let me add approximately. And so if we come back up here to our derivation, we can see where we did that. Essentially, we would just be ignoring all of these here. And then, of course, we have ICR is equal to IREF as claimed there. But, of course, that's approximate because we're neglecting base currents. So now into sort of some implications in terms of what does this mean? Why is it useful to put all of these transistors together? Well, one thing is that we could combine these various outputs in order to get different values of currents. So maybe we want some value of current greater than our IREF. Maybe we want something 3 times greater than IREF. So we have IREF designed to be 1 milliamp, but we want to power something that's 5 milliamps. Well, so what we could do is we could combine 5 of these transistors together so that all together they're providing 5 milliamps to our load. So what we can do is we can combine outputs to get a larger output overall. So let's say a larger overall output, and that's compared to our IREF. Because with all of our other configurations, we're approximately at IREF, or for the case of our Widlar current source, we're actually a lot smaller than IREF. And so we can use different groups of transistors or different transistors to bias different loads as well. So we don't necessarily have to use every transistor to bias a certain load. Maybe we use 2 transistors to bias load A, and transistors 3, 4, and 5 to bias another load. So we can sort of mix and match, and that gives us a little more freedom in our design. So just a couple other things that I want to mention quickly about our multi-transistor current mirrors here. The first thing is our circuit symbols. So of course you don't want to have to be drawing all of these transistors out each time. So for instance, if we have a 2 transistor current source, what we can do is we can write sort of 2 emitters here. So we write sort of 2 little arrows, and then we have those connecting together, and then that's connected to whatever we have coming out of here. So this would be if we had 2 transistors. And so the idea scales up. Of course, if we added 3, we would just have sort of 3, and so that should be connected. We would have sort of 3 arrows coming out. And so we draw an arrow on each of these because they're all our emitter. We connect them down here like this, and that would go to where we want, and then this would be our collector. So of course, at sometimes you might have enough that it becomes tedious even to draw out this many arrows. So maybe you just draw in here that you have an arrow for our emitter, and then you have a dot, 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 and then you have another arrow coming down here, and you would say that you have N transistors there. So if you ever see that in a circuit diagram, that's what that is referring to, sort of 2 transistors connected how they are in this multi-transistor current mirror. One other thing I want to note is that this multi-transistor current mirror is not ideal for discrete circuits. So not for discrete circuits. And so the reason for that is if we don't have matched transistors, what's going to happen is one of those transistors is going to end up carrying a lot of the current. Because remember, this whole analysis is based on the idea that we have matched transistors and we have the same VBE, therefore we have the same currents. If that's not true, however, we're going to end up with one of them carrying a lot of the current, for instance, maybe Q1, and of course that could lead to device destruction. So typically this is something that is only done if we're talking about ICs. So that's all we're going to talk about in terms of our integrated circuit biasing. As I've mentioned before, we could do comparable things with our MOSFETs, our field effect transistors. Because a lot of it is very similar and we have a lot of other material to get through, we're not going to spend time doing that in class. But of course, you're welcome to look through that in Neiman and to let me know if you have any questions about that.